So when I was coming up with this video, I was debating whether or not I should do a whole bunch of little 40-second, 45-second videos on the different nucleophiles that can displace the halogens and alkyl halides, or I thought what would be far more useful and I think more useful because it applies both to organic 1 and organic 2 is just talk about this general class of nucleophilic substitution. So in this case, I've drawn an alkyl halide and I want to replace it. In all cases, our nucleophile contains lone pairs, so it is a Lewis base. And it's going to act like a Lewis base by giving the lone pairs this carbon and displacing the bromine. Now, the bromine, or the halogen, if we're going to speak more generally, can lead by either an SN1 or an SN2 mechanism. And your preference for SN1 and SN2 is going to depend on whether it's a primary, secondary, or tertiary carbon. Do you have a high K dielectric salt? Do you have a protic solvent versus aprotic solvent? I have a whole video on this. So go consult that. We're not going to bother ourselves with whether or not it's an SN1, SN2, and more just talk about the end result of this reaction. But in all cases, if we want to have nucleophilic displacement of a halogen and an alkyl halide, we have to have a lone pair. And this is going to come in 3 flavors. First flavor is something that's going to look like an alkoxide. And I'm going to say looks like an alkoxide because occasionally it is an alkoxide. It's an alcohol without its hydrogen. Sometimes it's a carboxylic acid that's been deprotonated, sometimes it's OH. And those are our 3 scenarios here. R equals H, so hydroxide. R equals an alkyl group, so this is your alkoxide. And R is a carboxylic acid. In all cases, the oxygen is going to displace the bromine. So this is what's going to form, basically, the oxygen is going to serve as a bridge to whatever this R group is. Now, in the case of an OH, we can do this with sodium hydroxide, and we've seen this before with reactions of water and alkyl halides. We can definitely substitute halogens with OH groups if we have an OH group present. The alkoxide ones, though, where we have an RO group, these are the dangerous ones. And I say dangerous because alcohols are very good, alkoxides are very good bases. Alcohols are very bad acids. So if we have a bulky alcohol group, it's more likely to do elimination than anything else. So if you want to do substitution of an OR type, meaning that this R is some carbon chain, try to keep it so that's a primary alcohol, so you favor the displacement reaction, not the elimination. Now the carboxylic acid group, this is pretty much always going to do the nucleophilic attack. And the reason why I say pretty much almost always is that carboxylic acids, as their name implies, are really good acids. They're good at getting rid of that hydrogen, and they're not likely to take it back. So unless you're underneath low pH conditions, it's not likely that you got anything other than this O- group there to attack. Second flavor we can have are the thiols. So, or thiol-like compounds. So sulfur is going to act a lot like oxygen. The big issue is that sulfur is not nearly as acidic, or it's a much better base than something like the O-. So if we have an R equals H, typically what we'll get is the same thing with the hydroxide. The sulfur will displace the bromine, but unlike the OH groups, we're less likely to get the alkyl group to push it back off. We can also get alkyl groups. So if we have an alkyl group, we're going to get basically the sulfur equivalent of an ether. The sulfur is going to form a bond to this carbon, and then we're going to have a carbon chain hanging off of it. It's going to be similar to our alcohols. The last flavor of this is some carbanion, a carbon containing a lone pair. So we can see this with something like cyanide, Cn-1. We're going to get attacked. Now, the big thing about these types of nucleophilic attacks is they're going to be irreversible. Once we form that carbon-carbon bond, it doesn't break. Now, this can be generated in a lot of ways. Cyano group, we can deprotonate a terminal alkyne. So if this were something like C, this would also be able to do that. Or, and I'll talk about later in the video, organometallic complexes. So something where we have lithium Cr or a Grignard, CMG, Br. There's lots of possibilities here. So if we have an organometallic complex, assuming it is not so basic that it prefers the elimination reaction, this is also a very good way of doing displacement. So these are your three types of ways that you can do a nucleophilic attack. Now there are others. Definitely you can throw something like sodium iodide in there, and the iodine will displace the bromine. But in terms of more practical reactions, if our nucleophile contains an O with a minus, we can have an OH, an alcohol, or alkoxide because we remove the hydrogen, or carboxylic acid that's removed loss of hydrogen. For sulfurs, we can have an SH, or we can have a thiol. And for our carbon ones, we can have something like terminal alkyne, cyano, or some type of organometallic. The big thing with this last class, it's not reversible. Once we form that carbon reaction, we're done.